Okay, speed of sound. As I said, we know this value right here, 343 meters per second. That's the speed of sound in air, in normal conditions, right? Room temperature. So that's the sound that you're hearing right now as I'm talking. That's the sound that you hear, the velocity of that sound, right? 343 meters per second. Now, we can find the speed of sound in different situations. So right here, I have all the formulas that you need. I know it looks like complicated, all of these formulas, but I'm going to show you that actually it's really easy to apply these formulas, okay? The first one is the speed of sound in a fluid, like water, for example. It can be water or any other fluid. You will apply this formula right here. V, that's velocity, equals the square root of B over rho. Remember the rho was that Greek letter, right? The rho letter, and it is the density of the fluid. You already know how to find that one, and actually we have a table. We have a table with all the densities, right? And then we have B, capital B. That will be the bulk modulus. What is the bulk modulus? That is just a value that you can get from another table, and it's right here. Let me show you the table. Is this one. So this right here is bulk modulus, and you just need to know the material. So if the material is water, for example, you will use this value right here. You will come back and plug that value right here. So it will depend on the material that you are submerged, right? If it's water, you use this value, as I said. If it's mercury, you will use this value, right? So it's the same idea as density. It's just a table. You will go and get that value from that table, okay? So it's really easy, this formula. The next one is actually, we have two formulas, but it's just to find the speed of sound in a gas. So you can use either of those. It will depend on what is given. If they are giving you the molecular mass of the gas, that is M, capital M, you will use this formula. You will plug that value right there. If they are giving you the density, you can see right there, in the denominator we have density, then you will use this formula. But it's the same situation, right? The speed of sound in a gas. Everything else is just a constant. For example, R is the gas constant, and it will be this value right here. T will be the temperature that should be given. It should be given in the example or the exercise, okay? And this Y right here is the adiabatic constant. That's just a name, right? It sounds really strange, adiabatic constant, but it's again a constant that you will plug right here or right here. Then we have this speed of sound in a metallic rod. It will be this formula, and we have the Young modulus and the density of the metal again, right? So it will go, you will go to the table with all the densities and bring that value right here. But the Young modulus is the same as this one, the bulk modulus. You go to the table, you can see right here, Young modulus is now this part right here, and it will depend on the material again, right? If it is steel, you will use this value. If it's copper, you will use this value, etc. So you will take that value and plug that value right here. So it's really easy. This one and this one is the same idea. Go and look for that value and plug it there. Finally, we have the speed of sound in an extended solid. Again, this one will depend on the material right here, but the name is different. B is bulk modulus, S is shear modulus. This is the one, shear modulus, that you need to go and look right here, shear modulus, and find that number right here. Again, it will depend on that material right here. If it's steel, it will be this value. If it's copper, it will be this value. So you need to check that right there and plug it here. So it's really easy. Now, to show you that I'm not lying, that is really easy, I'm gonna solve this example right here. So you can see that it's just plugging the values into the formula. So in this example, they are asking me to calculate the sound speed in steel. So I know the material now. So I can go back right here. Steel is right here, and I will need the Young modulus. So it will be this value right here. That's why I have it right here. You can see it. I brought that value from that table right there. But I also need the steel density, is this value. Now, I don't have the table right here in this presentation, but you're supposed to know how to get that value, right? We have a table, you can go to Canvas, and we have a table with the densities. You just go and look for steel and bring this value, right, for density. And that's it. You have the two values that you need. You plug the values right here into the formula, and that's it. You have this. That's the speed of sound in steel, 5,044 meters per second. Now they are asking for another thing right here. B says calculate the proportion of this speed regarding to the sound in air. So they are asking how faster is going or how slower is going compared to the speed of sound. How can you do that? You just need to divide the velocity, the speed of sound in steel, this one right here, over the velocity in air, the speed of sound in air. So we know both now. You do that calculation, and it will give you this, 14.71. Now, how can I find the proportion? You just need to move V air is down here in the denominator. You move it to the other side, and it will be here. You can see it. It will be like this. So now you know that the speed of sound in steel, this one, is the same as 14.71 times the speed of sound in air. So you can say it like this. The speed of sound in steel is 14.71 times the velocity in air, or faster than the velocity in air, that's the speed in air, right? So that's the difference. It's a lot faster, 14.71 faster, right? The speed of sound in steel. So that's the proportion right there. Now you can see it's really easy to find that velocity. Just plug in the values into the formula. And I have this exercise right here. Like I said, I'm not going to give you extra work because you are working with the activity, with the exercises from the activity. But I just want you to show you, I just wanted to show you right here something. Is the only difference is that it's water now. So look how easy it is. You go back, and because it's water, it's supposed to be this, because it's a fluid. So now it's just changing the formula. It will be this formula, right? And B is the bulk modulus. You go to the table. Right here is water. You see it, water, and bulk modulus is right here. So you will use that value right here. And then right here, you need the density of the water in this case. And that one is easy. You go to the table and it's 1,000 kilograms over meter cubed. We have used that value before. So you will plug those two, and that's it. That will be the velocity. So it's really, really easy to find those right there, those velocities. Okay, it's like this one. And for this one, calculate the proportion. It will be the same as this. You will divide them and then move the one in the denominator to the other side, and it will tell you how fast there is going, right? And that's it. That's my presentation right here. Now I'm gonna take the attendance.